The early evening sky over Melbourne Airport was low and heavy, a leaden blanket pressed down by the late summer heat. The air smelled faintly of tarmac and jet fuel, mixed with a metallic tang of distant rain. On the apron, a DC-9 of Trans Australia Airlines sat in quiet readiness, its fuselage gleaming under the pale amber of the runway lights. Engines idled, producing a low hum that seemed almost contemplative against the vast expanse of concrete and shadow. Inside the cockpit, instruments glowed in soft green and amber. The pilots ran through checklists, their voices measured, clipped, professional. Outside, the wind shifted subtly, carrying with it a hint of turbulence from the nearby Yarra River. Visibility was within operational limits, yet the approach ahead demanded precision. Melbourne's Runway 16 approached with a long glide over urban terrain, a margin for error thin, unforgiving. The passengers were mostly unaware of the nuances at play. Seats reclined, magazines unopened, coffee cups balanced on trays. On the flight deck, time seemed to stretch and compress simultaneously. Every decision, every minor correction, carried weight. The aircraft taxied into position, aligned, and began its descent, engines humming, spoilers armed, flaps extended. The world outside had narrowed to a narrow corridor of concrete, lights, and shadows. As the DC-9 cut through the evening haze, the camera lens would linger on the wings slicing through humid air, instruments flickering with each adjustment, and the pilot's hands moving methodically across controls. Silence dominated the cabin, punctuated only by the low whine of engines, the occasional radio call, and the almost imperceptible vibration of tires on dampened runway lights ahead. This was not just a flight. It was a convergence of human skill, machine precision, and environmental chance. Moments like these define aviation, not by the flights that arrive safely, but by the chain of circumstances that can unravel within seconds. Trans Australia Airlines, or TAA, was a cornerstone of Australian aviation in the late 20th century. Established in 1946, it had built a reputation for reliability and professionalism, connecting cities across the continent. By 1996, the airline operated a mixed fleet of jets and turboprops, including the McDonnell Douglas DC-9, a workhorse of short to medium-haul domestic routes. The DC-9 was a twin-engine, narrow-body jet designed in the 1960s for efficiency and simplicity. Its cockpit was deliberately functional, with analog gauges and early digital readouts, emphasizing procedural flying and crew discipline. Pilots were trained extensively on approach and landing protocols. Yet like all aircraft of its era, the DC-9 demanded precise manual input during critical phases of flight. Automation could assist, but not replace, human judgment. Melbourne Airport, situated near the Yarra River and a patchwork of urban sprawl, presented a mix of operational opportunities and constraints. Runway 16, the primary landing strip for westerly approaches, stretched long but required careful navigation over residential areas, occasional crosswinds, and subtle elevation changes. Pilots were accustomed to these conditions, but the margin for error was narrow, particularly at night or under challenging weather conditions. TAA's crews were experienced professionals, trained rigorously in cockpit resource management and standard operating procedures. They worked in teams. Captain and first officer shared responsibilities for checklists, monitoring systems, and communication with air traffic control. Despite the procedural safeguards, aviation is inherently human, and the smallest deviations, misread instruments, timing errors, environmental surprises, could cascade. The airline operated in an era when aviation was transitioning. Modern avionics and safety systems were emerging, yet older aircraft like the DC-9 remained vital. Operational pressures, schedule adherence, and the demands of a growing domestic network meant that each flight carried a quiet tension, a balance between routine and the unexpected. For the passengers aboard that fateful flight, these details were invisible. They only saw a standard domestic service, a familiar aircraft, familiar airline, a journey expected to be uneventful. But the stage was set, and every element, from aircraft design to airport layout, crew training to environmental conditions, would converge in a sequence that would test all systems and human judgment. The DC-9, by 1996, was a proven design, known for simplicity and reliability. Its systems, while not cutting-edge by modern standards, were robust, redundant hydraulic controls, twin Pratt & Whitney JT8D engines, and a cockpit designed for hands-on management. The aircraft demanded attentiveness. Autopilot could manage the descent, but the approach and landing phases required careful monitoring of airspeed, glide path, and flap configuration. The captain on this flight was an experienced aviator, with thousands of hours logged on both jet and turboprop aircraft. Calm under pressure, meticulous in checklist discipline, he had earned the respect of peers and subordinates alike. The first officer was younger but competent, fully trained on the DC-9 systems and Melbourne Airport approaches. Together, they had flown multiple sectors that day, managing tight schedules and the inevitable minor disruptions that characterized domestic operations. Cockpit resource management was standard, conversations measured, roles clearly divided. Environmental conditions that evening were benign but subtle. Low-hanging clouds created diffuse lighting, and intermittent crosswinds brushed the final approach corridor. The runway was fully operational, lighting systems functional, and visibility within acceptable limits. Yet in aviation, small variables, slightly stronger gusts, subtle drift from intended glide path can amplify when combined with human factors. The surrounding urban terrain, river pathways, and rising hills to the east required precise alignment to maintain a safe approach corridor. Systems interplay was critical. The DC-9's glide slope indicators, altimeters, and airspeed sensors provided multiple layers of feedback. The crew monitored engine thrust, flap positions, and rate of descent, cross-referencing instruments with visual cues. Any discrepancy had to be detected immediately. Minor deviations could cascade into more serious misalignment. Human and machine functioned as a single system, interdependent and sensitive to timing and decision-making. The convergence of aircraft, crew, and environment is where accidents emerge. Here, there was no single failure. Instead, multiple small vulnerabilities existed in parallel. Procedural flexibility, environmental subtlety, operational pressure, and system limitations. This section of the narrative lays a foundation for understanding how the DC-9's final descent would unfold, and how each factor, aircraft performance, human decision-making, and environmental nuance, interacted in a precise, high-stakes chain. The DC-9 had begun its final descent toward runway 16. The engines hummed steadily, flaps fully deployed, spoilers armed, and landing gear locked. Outside, the evening light had deepened. Clouds diffused the last rays of sun, casting a muted glow over the runway. The crew monitored instruments meticulously, altimeters ticking downward, airspeed steady, glide slope indicator centered. As the aircraft approached the threshold, subtle variations began to emerge. Crosswinds nudged the plane slightly off the ideal centerline. The first officer noted minor deviations, and the captain made small corrections, relying on both visual cues and instrument feedback. The DC-9, responsive yet unforgiving at low altitude, required precise alignment. At approximately 300 feet above ground, the aircraft descent rate briefly exceeded the optimal profile. The captain responded with incremental thrust adjustments, but the combination of wind, slight misalignment, and human timing lag created a narrow window of reduced situational margin. Instruments reflected a controlled descent, but the visual reference to the runway edge was fleeting, obscured intermittently by haze and low clouds. The final seconds unfolded quickly. The aircraft touched down slightly off-center, the main wheels meeting tarmac before the nose. Braking systems deployed normally, spoilers extended. Yet, despite procedural inputs, the plane began to track laterally. The tires skidded over the damp runway surface, resisting directional control. The cockpit crew responded instantly, attempting corrective rudder and brake application. In this delicate moment, milliseconds dictated outcomes. The DC-9 came to a stop beyond the intended touchdown zone. No catastrophic breakup occurred. No explosive events were recorded. The aircraft was intact, but the excursion had resulted in substantial structural stress and system damage. Emergency protocols were initiated, and ground personnel approached with caution. In retrospect, The accident sequence was a textbook illustration of loss of situational awareness compounded by environmental subtlety and operational pressures. This moment encapsulates aviation's inherent complexity. Trained professionals, a capable aircraft, and fully functional systems, all challenged by the interplay of timing, environment, and decision-making. The narrative is not one of blame, but of how multiple small factors converge to exceed margins of safety, producing outcomes that are sudden yet comprehensible in context. Once the DC-9 came to a halt, Melbourne Airport activated its emergency response protocols. Fire crews, medical teams, and airport security moved swiftly, assessing the aircraft and passengers. Remarkably, there were no fatalities, but several occupants sustained minor injuries. The event, though contained, prompted a thorough investigation to understand how a routine landing had resulted in a runway excursion. The Australian Transport Safety Bureau, ATSB, responsible for civil aviation investigations, initiated a meticulous review. Investigators examined flight data recorders, cockpit voice recorders, maintenance logs, and air traffic control transcripts. Physical evidence from the runway, skid marks, tire condition, and surface friction, was analyzed to reconstruct the aircraft's final moments. Weather reports and wind shear measurements were cross-referenced to confirm environmental conditions. The investigation revealed a chain of contributing factors rather than a single point of failure. Slight misalignment on final approach, minor overcorrection of thrust, and subtle crosswinds combined to reduce the aircraft's margin for safe landing. The DC-9 systems operated within normal parameters, and the crew followed standard procedures. However, the interplay of human response and environmental nuance exposed vulnerabilities inherent in short, low-altitude approaches under marginal conditions. Recommendations were multi-layered. The ATSB highlighted the need for enhanced crew training on precision landings under crosswind conditions, improvements in runway friction monitoring, and better integration of visual approach guidance at Melbourne Airport. TAA reviewed operating procedures, reinforcing cockpit resource management and emphasizing strict adherence to stabilized approach criteria. These adjustments would ripple across Australian domestic aviation, influencing both airline policies and airport safety protocols. The incident left a quiet but lasting impression on the aviation community. Pilots, engineers, and regulators reflected on the event not as a sensational story, but as a reminder that aviation safety depends on the meticulous coordination of aircraft, crew, and environment. Lessons learned were translated into procedural improvements, ensuring that similar scenarios were less likely to escalate into accidents in the future. In the months following the Melbourne Runway Excursion, aviation authorities, airlines, and pilots reflected quietly but thoroughly on the lessons the event offered. TAA integrated procedural revisions into training programs, emphasizing stabilized approach criteria, crosswind correction techniques, and reinforced cockpit resource management principles. The DC-9 fleet underwent additional briefings on operational margins during final approaches under variable environmental conditions. At Melbourne Airport, runway monitoring and visual guidance systems were re-evaluated. Subtle improvements, better lighting alignment, enhanced friction measurements, and periodic simulation of marginal condition approaches were introduced to reduce the risk of deviation. Air traffic control protocols were updated to provide more precise wind advisories during final descent, ensuring crews had the clearest possible situational awareness. The legacy of the 1996 DC-9 incident was not in headlines or dramatic narratives, but in quiet, systemic change. Pilots reported greater confidence in handling subtle deviations. Airport authorities felt more secure in their oversight. Engineers and regulators documented safer procedures. The convergence of aircraft, crew, and environment had revealed vulnerabilities, and the aviation system responded methodically, thoughtfully, and successfully. For passengers and crew, the event became a reminder of the precision required in commercial aviation. For the industry, it became a case study in the accumulation of minor factors that, if unchecked, could escalate. Yet the outcome, survivable, instructive, contained, demonstrated that a combination of skilled human response, technical reliability, and methodical post-event analysis could transform a near accident into a blueprint for safer operations. In the end, The narrative closes quietly. No explosions, no dramatized heroics. Only the continued pursuit of safety, the refinement of procedures, and the unwavering professionalism of those who keep the skies secure. Lessons were learned, systems improved, and aviation moved forward, guided by the careful, deliberate reflection that events like this demand.